Good afternoon, everyone. Let's wait for 5 minutes before we start the session. Okay, so today is our last tutorial session for this course. We'll be discussing some problems related to nonlinear space. And before that, let me go back to that problem we left in the previous session, which was as follows. Mm, Yeah, state true or false if f from R to R is differentiable everywhere and uniformly continuous. Uniformly continuous. Then they're saying that the derivative must be bounded. So before discussing the solution for this problem, I would like you to recall we actually did a result related to the uniformly continuous functions. You can go back to the problems related to uniformly continuous functions. There we had discussed this result that if f is differentiable and there exists some m positive such that mod f dash x is less than equal to m for every x belonging to our domain, whatever the domain is, then f is uniformly continuous. It says that if a function is differentiable and the derivative is bounded, hence the function is uniformly continuous. But the fact is that the converse of this result does not hold. Which is the statement of our problem. What does the converse says? Converse says that if f is differentiable and suppose it is uniformly continuous also, then they are saying that the derivative must be bounded. That need not be true. Differentiable with bounded derivative implies uniformly continuous. But differentiable with uniform continuity need not imply boundedness of the derivative. That's what the aim of this problem is too. That means they want you to understand this fact that this results holds in one direction but not conversely. Continuous. And I would highlight that this does not hold the converse part. So now since I'm saying that the converse does not hold, I should be able to give you some exact example. That's what I was not able to provide you in the previous session. Today, yeah, I'll at that time I was a bit confused about the example. The A good example would be this f of x equals to, so let me write it properly. Consider the function f from R to R defined as follows. F of x is equal to x square sine 1 by x square for x non-zero, 0 for x 0. Okay, I'll firstly claim that. Clearly, you can check it yourself. F is differentiable with what will be the derivative? The derivative at for x non-zero, this is directly we can use the product rule. X square cos 1 by x square minus 2 by x cube plus sine 1 by x square times 2x. Now this is equal to minus 2 by x cos 1 by x square plus 2x sine by x square. Clearly, this function is unbounded when x is near 0 due to this part. So therefore, the derivative is not bounded. F dash is unbounded. Okay. Yeah, this goes to infinity or minus infinity as x goes to 0. Clearly, you can also try to plot this function. So this is unbounded. It is unbounded near 0. Since limit x tending to 0, 2 by x cos 1 by x square is bounded, so it won't affect anything. This will be infinity, and limit x tending to 0 to x sine 1 by x square, this will be 0. Now next we claim that this f is uniformly continuous. Well, for that we will use above result. Let's see how. Okay. Now limit x tending to infinity fx, which is, of course, as x tends to infinity, fx is just x square sine 1 by x square, which is limit x tending to infinity sine 1 by x square on 1 by x square, which can be written as limit h tending to 0 sine h by h. We know that this is equal to 1. Oh, and f dash x, which is equal to yeah, x square plus 1 square plus 2 by x cube plus sine 1 by x square to x. Okay. Limit x tending to infinity f dash x is equal to limit x tending to infinity minus 2 1 by x cos 1 by x square plus 2x, or in fact I can write it as 2 sine 1 by x square x times 1 by x square. So this will be minus 2 limit x tending to infinity 1 by x cos 1 by x square plus 2 limit x tending to infinity 1 by x sine 1 by x square 1 by x square, which can be written as minus 2 limit h tending to 0 cos h times h plus 2 limit h tending to 0, because as x goes to infinity we can take 1 by h to be equal to 1 by x, and as x goes to infinity h goes to 0. This is h times sine h by h. We know that limit h tending to 0 sine h by h is 1, and limit h tending to 0 cos h is also 1. Yeah, cos 0 is 1 because. Okay, so that means this is equal to minus 2 No, 0, 0, 0. Minus 2 times 0 plus 2 times 0. That means the derivative f dash x, limit x tending to infinity, f dash x is equal to 0. That means the function f dash is bounded, or in fact, okay, let's use the definition of this limit. This implies for epsilon, taking epsilon to be precisely 1, of course corresponding to this epsilon there will exist a real number k in R, such that this mod f dash x minus 0 will be less than epsilon, and epsilon is equal to 1 for all x greater than equal to k. This is just basic definition for limit extending to infinity f dash x equals to 0. The epsilon delta definition corresponding to the statement. That means mod f dash x is less than 1 for all x belonging to k to infinity. This implies, now since f is differentiable in k to infinity and mod f dash x is bounded for all x in k to infinity, this implies by above result, f is uniformly continuous. Okay, continuous in k to infinity. Similarly, you can try this yourself, as this limit extending to minus infinity, f dash x will be 0. Check yourself. And hence, exactly as done above, and hence f is uniformly continuous, uniformly continuous in some minus infinity to say, what do we take, k, t, suppose t. Okay, whatever this t can be small enough, that's not our issue. And so therefore on the number line, this minus infinity to infinity, the function is uniformly continuous here, the function is uniformly continuous here, and in between, since the function is continuous and on this compact domain, obviously it will be uniformly continuous. Also, since f, of course you can see that this is a continuous function, right? Even at 0, at x equals to 0, the limit will be exactly equal to 0. Therefore, the function is continuous everywhere. Since f is continuous on closed interval t to k, and we know that a continuous function on compact domain, a continuous function on closed and bounded domain is always uniformly continuous. F is uniformly continuous in t to k, and hence f is uniformly continuous on whole R. Therefore, this function f is uniformly continuous, differentiable, but the derivative is not bounded. The derivative actually blows up near 0. Hence, the given statement is false. I hope this example is clear with you, whatever. Hmm. I hope this example is clear how this is explaining the fact that the given statement is false. So the main idea is that if f is differentiable, It is uniformly continuous if the derivative is bounded, but if it is uniformly continuous, that does not imply the derivative is bounded. That means if we suppose we have a differentiable function, its boundedness of derivative will imply uniform continuity, but uniform continuity need not imply the boundedness of the derivative. I hope this is fine with everyone. Please go through the proof again. If you have any doubt at any step, you can ask. I'll wait for 5 to 10 minutes. Okay, so if there is no doubt, let's move ahead. Question number 2. State whether true or false. Let V be the vector space that contains all continuous functions defined from closed interval 0 to 1 with the usual sup norm. So let me just give you the definition of the sup norm. So the vectors in this vector space are actually continuous functions. And if we define the sup norm over any vector in this vector space, this is equal to supremum mod fx for x belonging to closed interval 0 to 1 for every f belonging to V, which is C0. Okay, so now let Fn be a sequence in this vector space, that means a sequence of continuous functions, be a sequence such that each of this Fn is defined to be equal to sine to the power n pi x. They're saying then the sequence Fn is Cauchy. So we need to see that whether this sequence is Cauchy or not. So firstly, before directly hitting on to Cauchy or convergence, let's observe these functions. So we have for n equals to 1, this is f1x, which is equal to sine pi x. Similarly, f2x will be sine square pi x. Now, since the value of the function sine is always in between -1 and 1, and we are taking, that means sine pi x is something lesser than 1. And its square will always be less than sine pi x. How am I saying this? Because, see, our domain x is in between 0 and 1. So pi x is in between 0 and pi. And in between 0 and pi, we know that the function sine pi x is positive. That means sine pi x is obviously positive, and this will be less than 1 also. That means this value sine pi x is always in between 0 and 1. And we know that for real numbers, if a real number is in between 0 and 1, its square will always be lesser than that number. That means this gives us that f2x is less than equal to f1x. In fact, you can see that again f3x will be sine cube pi x, that will be less than equal to sine square, because everything is in between 0 and 1. So basically we have this reverse inequality because this turns out to be a decreasing function. So that means f3x will be less than equal to f2x, less than equal to f1x, and so on. Okay, yeah, this happens for every x in closed interval 0 to 1, and so on. So now let's try to plot these functions. So we have 0, 1, and between is somewhere 1 by 2. Now since x at x equals to 1 by 2, pi x is pi by 2. So we know that pi by 2, sine pi by 2 is 1, whatever the power will be. So that means now since f1x was sine pi x, the graph would be something like this. F2 is sine pi x square. That will be, sorry, that has values lesser than f1x, but in between 0 and 1 and exactly equal to 1 at 1 by 2 because square of 1 is also 1. And in fact, you can observe that as you move forward, the functions are something like this. At x equal to 1 by 2, the values will be 1. So, can you expect what will be the pointwise limit of this sequence? So clearly, at x equals to 1 by 2, f n x is equal to 1 for every n in n. That means the sequence this f n 1 by 2 will converge to 1. For rest of the x, you can observe that we are going towards 0. And for every x not equal to 1 by 2, x in between, or in fact I should write for every x in 0 to 1 minus 1 by 2, this f n x, which is sine pi x to the power n, will go to 0 because sine pi x is strictly less than 1 for x not equals to 1 by 2, and we all know that for any fixed strictly less than 1 alpha, alpha to the power n goes to 0 as n tends to infinity. So that means if we define function f(x) to be 0 for x not equal to 1 by 2 and 1 to at x equals to 1 by 2, then f is the pointwise limit of the sequence. F n x converges to fx pointwise. But this is what they are talking about pointwise limit. What we need to check is this Cauchy-ness in this space. So what do we mean by a sequence? Yeah, this was just for your understanding how these functions are working. So let me just give you an idea of, in fact, I should write definition. When do we say a sequence is Cauchy in this vector space? A sequence Fn in C01 with sup norm, this is our nonlinear space, is said to be Cauchy if for any epsilon positive we can find delta positive or sorry, not delta. We can find a stage n in n such that instead of modulus, what modulus we had in this case of real sequence of real numbers, now we have the norm. If you remember, I told you while introducing you with the term norm, that norm is kind of generalization of modulus. Whatever modulus does in the real line, norm does in abstract spaces. So this will be Fn minus Fm norm is less than epsilon for all n and m greater than equal to n. If this condition holds, then we say that a sequence is Cauchy. Now, in our case, we will see that actually this is not a Cauchy sequence. I'll explain you how. Okay. So, okay, claim that the sequence Fn is not Cauchy. For every n in set of natural number, let xn be the point in closed interval 0 to 1 such that Fn at xn is exactly equal to 1 by 2. We can always find such an xn because see what do we need to this is somewhere in between is 1 by 2 if we take this line. So for f1 this will be our x1. For f2 we need to find x2 such that at that point the function attains value 1 by 2. So this will be our x2 and this will be our x3 and so on. We can always find such an xn. We'll see how this will be helpful for us. And of course, if at x1, we can see what I was saying, that if fn at xn is equal to 1 by 2, then fn plus 1 at xn, that means f2 at xn will obviously less than fn at xn. And in fact, all other fn's will be less than at fn at x. I hope this is clear. What I'm saying is that if we found, suppose say, yeah, let's look at it again. See, at x2, we know that the function f2 attains 1 by 2. And at x2, what can we say about rest of the functions after that? That means f3 and f4, they all are lesser than f1. So that can be written as this fn plus m is less than equal to fn for all m positive. So that's what we will be using. Okay, that means fn plus m at xn is strictly less than 1 by 2 for all m positive. Clearly by construction, or we can say by the definition of the sequence. Okay, uh, we need to see the sup norm of course, when we take arbitrary n and m can be written as n plus some k. Yeah. Instead of m to make it more easy to understand, let's take this way. Let n and m belong to n be arbitrary, and without loss of generality, we can assume this m to be strictly greater than n. That means m can be written as n plus k for some k positive, obviously. So that means norm fn minus fm, sup norm, which is equal to minus fn plus k, and by definition this is equal to supremum mod fn minus fn plus k at x for x belonging to close 0 to 1. Obviously this will be greater than equal to the value at some point, say any 1 by 2. This will be greater than equal to fn minus fn plus k at 1 by 2, because this is actually the supremum over all domain and this is just a value at one point. So obviously this will be lesser than the supremum. So now this is equal to Fn at, oh, not at 1 by 2, sorry, at Xn. Fn at Xn minus Fn plus K at Xn, which is equal to 1 by 2 I'm sorry for the disturbance. Okay, so this is equal to 1 by 2 minus okay, Fn plus K at Xn. Now taking n tending to infinity or K tending to infinity. Okay. So instead, K tending to infinity, we get Fn minus Fn is greater than equal to 1 by 2 minus 0, which is equal to 1 by 2. But if Fn was Cauchy, in that case, we should have got Fn minus Fm goes to 0 as n and m goes to infinity. So clearly, as k tends to infinity, m is also going to infinity. No? So that gives us a contradiction. Thus, by contradiction, Fn can never be a Cauchy sequence. Therefore, the given statement is false. I hope this is clear. How we get this sequence to be non-Cauchy, even though it has pointwise limit, but this is not a Cauchy sequence in the space of continuous functions with the supremum law. If you have any doubt, you can ask. I'll wait for 5 minutes. Okay, so if there is no doubt, let's move ahead. Question number 3. Now let V be the space of all continuous functions defined on closed interval 0 to 1 with some other norm. We call it L1 norm, which is defined as norm 1f is equal to integral 0 to 1 mod ft dt. Clearly, since any function f in C01 is continuous on closed and bounded domain, closed and bounded interval 0 to 1, it will be obviously always be integrable, and therefore this norm is well defined. Now they are saying that then the sequence Fn is Cauchy, where this is defined, this Fn, x is equal to x to the power n for all n and x in closed interval 0 to 1. So they are saying the sequence of functions x to the power n is Cauchy, where when the norm considered is this L1 norm. So let's see whether this will be Cauchy or not. So let n and m be any natural numbers without loss of generality. We can assume one to be bigger than the other one. Then Fn minus Fm L1 norm is equal to integral 0 to 1 mod Fn minus Fm t dt, and this is equal to 0 to 1 mod Fn t minus Fm t dt, which is equal to, by the definition, t to the power n minus t to the power m dt. Now okay, um, since t is in between 0 and 1, that means, and this n is greater than m. So this gives us t to the power n will be less than equal to t to the power m. That means t to the power n minus t to the power m is negative. That means this modulus t to the power n minus t to the power m, this is equal to t to the power m minus t to the power n. That means this is equal to 0 to 1 t to the power m minus t to the power n dt. Now let's just integrate it. This will give us t to the power m plus 1 upon m plus 1 minus to t to the power n plus 1 upon n plus 1, 0 to 1. This will be 1 upon m plus 1 minus 1 upon n plus 1. We all know that this goes to 0 as both n and m goes to infinity. That means this norm Fn minus Fm L1 norm goes to 0 as n and m tends to infinity, which in terms of epsilon definition can be written as, for any epsilon positive, there exists a stage n in n such that mod, taking mod over norm again, that's same, Fn minus Fm is less than epsilon for all n and m greater than or equal to capital N. Now this is the definition of Cauchy sequence. Therefore, the sequence Fn is Cauchy in the space C01 with the L1. So I hope you are able to understand the importance of norm. Whatever the norm is defined on the space, how it is affecting the Gaussianness of the sequence. Please go through the proof again. If you have any doubt, you can ask. Okay, so let's move ahead. Question number 4. Yeah, in this problem, I would like you to introduce with another nonlinear space that we call the LP space, the space of all sequences. Okay, for equal to infinity as well. We define the space LP to be space of all those sequences Xn. This is a sequence of real numbers such that summation n from 1 to infinity, summation n from 1 to infinity mod Xn to the power p. This is finite. And this is for p greater than equal to 1 less than infinity. And we define L infinity to be the space of all bounded sequences. Mod Xn is less than equal to m for every not this m is not fixed. Xn is a bounded sequence. And consecutively, we define this norm, LP norm, to be summation n from 1 to infinity mod x into the power p all to the power 1 by p for all 1 less than equal to p less than infinity, where this x represents the sequence x1, x2, x3, and so on. And this infinity norm is just the supremum. Of course, since the sequence is bounded in an infinity, this supremum must exist. Supremum mod xn, where xn belongs to, yeah, xn is the sequence. Again, same. So for these LP space, we have the following result. Show that this show that L1 is contained in all LPs less than equal to p less than equal to infinity. The space L1 will be the space of sequences xn such that this summation for p equals to 1, that means just mod xn, this will be finite. If this happens, then it should belong to all other LP spaces as well. So we'll see how to prove this. I hope this is clear how we define the LP space and the norm over those spaces. So these are called sequence space because the vectors in this space are actually the sequences. Okay. We start with first case, p equals to infinity. So we claim that L1 is a subset of L infinity. So in order to show that a set is subset of some other set, what do? We start with an element in the smaller one. Here we will start with an element in L1 and show that this should be in L infinity. So let X be an element in L1. Now since X is an element in L1, L1 is the space of sequences, then that means X is a sequence. X is a sequence, Xn, such that mod xn, n from 1 to infinity, this is finite. Now, since the series is convergent, now since the series summation n from 1 to infinity mod xn is convergent. We all know that if a series is convergent, that means the corresponding sequence converges to 0. Mod xn, this converges to 0 as n tends to infinity. And for convergent sequences, we all know that if a sequence is convergent, then it is always bounded. That means the sequence mod xn is bounded. Since every convergent, in fact, since mod xn is converging to 0, that means mod xn will also converge to 0. So this modulus will not be any issue. Every convergent sequence is bounded. Now, since the sequence is bounded, that means it belongs to L infinity. So we started with an element in L1, which ended up it being in the space L infinity. That means L1 is a subset of L infinity. Next, in case 2, we will see what happens when P is strictly in between 1 and infinity. Okay. Again, we will start with the fact that X is in, let X is in LP. That means summation n from 1 to infinity mod xn. This is finite, and which implies that the sequence xn converges to 0. Obviously, because the sequence corresponding to a convergent series converges to 0. Now, since this converges to 0, that means corresponding to epsilon equals to 1, for epsilon equals to 1. Obviously, for every epsilon, we can find a stage. Na? So taking epsilon specifically to be equal to 1, there exists a stage n naught in n such that this mod xn minus 0, this is less than 1 for all n greater than equal to n naught. That means mod xn is less than 1 for all n greater than equal to n naught. That means mod xn to the power p will be less than mod xn for all n greater than equal to n, because if a real number is less than 1, its power p will be wait a second. Okay, yeah, because we know that if a real number is between 0 and 1, x to the its power p will be less than its power 1 for all for p greater than 1. Now that means this summation n from 1 to infinity mod x to x n to the power p, this is equal to summation n from 1 to n naught mod x n to the power p. This is just a finite sum plus summation n from n naught to infinity mod x n to the power p. This will be strictly less than summation n from 1 to n naught mod x into the power p plus, from, let me mark this as equation 1. Summation n from n naught to infinity mod xn. This is by first. Okay. Now, since this is just a finite sum, so this is bounded, and this sum is finite because mod xn, because x is a sequence in L1, so therefore this is finite. Since xn belongs to L1, that means this mod xn, n from n naught to infinity, is finite. That means the series mod xn to the power p is finite, which implies x belongs to n. So we started with an element in, oh sorry, this was L1. So we started with an element in L1 and ended up getting it in LP. That means L1 is a subset of LP. I hope this solution is fine. If you have any doubt, you can ask. I'll wait for 5 minutes. Okay, so if there is no doubt, we can move ahead. Question number 5. Let B be the space of all uniformly continuous bounded function. We denote it by BUC over R. It's the space of all bounded and uniformly continuous functions on R with the sup norm as we defined earlier. Norm, which is this supremum mod fx x in R. Okay. Now further, for any h in R minus 0, we define the function phi h f at any point x. This is equal to f of x plus h minus f of x on h for every x in R and f in V. So basically this phi h is a function which is defined from V to V to V, and phi h of f. Now this is in V, yeah, because our codomain is V. That means phi h f is a bounded continuous uniformly continuous function which is defined at any point x to be equal to this fx plus h minus fx by h. I hope this is clear how this phi h is defined. Then we denote we take this w to be the set of all those functions f in V such that phi h f converges to V, converges phi h f. Now phi h f is a collection of functions and this converges in V as h tends to 0. That means phi h f goes to some finite value as h goes to 0. All those f's are collected in the space W. Now they're saying that if f belongs to W, show that this f is differentiable and f dash belongs to V. Second part, show that if f belongs to V, f belongs to V is differentiable, then and f dash is in V, then f belongs to W. Let's tackle the problems one by one. So firstly, it says that if f belongs to W, then f should be differentiable. Let's start with f being an element in W. That means phi h f is convergent as h goes to 0. That means, now if we are talking about convergence, this phi h f is a function. So this is a sequence of functions. As h goes to 0, that means it is converging to some function. That means there exists some g in, of course, V, because everything is in V, such that, and what is the norm on V? The soup norm. Phi HF minus G, the soup norm goes to 0 as H tends to 0. Or in terms of epsilon delta definition, we can say that for any epsilon positive, there exists delta positive such that this norm phi HF minus G, soup norm, is less than epsilon whenever mod this H is less than delta. Okay, that means 0 is equal to limit H tending to 0 norm FH phi HF minus G, which is equal to, yeah, one thing you should have noticed now, that this gives us that phi HF is converging to G uniformly. Now, yeah, I should write that specifically. That means phi HF converges to G uniformly as H tends to 0. And we all know that uniform convergence implies pointwise convergence, not conversely. Pointwise never implies uniform convergence, but yeah, if we have uniform convergence, then we have pointwise convergence as well. That means phi HF at X converges to Gx for every X in, what is our domain? X in R. That means 0 is equal to limit H tending to 0 mod phi H f x minus gx. Now, by the definition of this function phi, this is equal to mod fx plus h minus fx on h minus gx. And what does this mean? This means that limit h tending to 0 fx plus h minus fx upon h is equal to gx, because this gx is independent of h. That means now, since this whole term was going to 0, that means this was exactly equal to gx. That means f is differentiable. Now, this is the definition of differentiability. No? Differentiable at x and f dash x is equal to g. And we know that this G belongs to F, the G belongs to V. We started because we had this convergence that gave us a function in V. And since G belongs to V, this implies F dash belongs to V. Therefore, we get that any function in W is differentiable and its derivative will be an element of V. Next, part B. Which says that if f is in V and it is differentiable, yeah, if f is a function which is differentiable and its derivative is also in V, this is V, then f should be in W. Let's see. Let f be an element in V such that f is differentiable and f dash belongs to V. we need to show that this we need to show that F belongs to W. That means the sequence phi h f converges to some g in V as h goes to 0. Okay, so now since f is differentiable, clearly there will exist some g in V such that f dash x is equal to gx. We were already given that the derivative is in V, therefore this g is in V. That means limit h tending to 0, fx plus h minus fx upon h, this is equal to gx for every x in R. Okay, now let x belonging to R be arbitrary. Then by mean value theorem, f x plus h minus fx upon h, this is equal to f dash xi for some xi in x to x plus h, which is equal to g xi, because yeah, f dash is equal to g. That means mod fx plus h minus fx upon h minus gx, this is equal to g psi minus gx, which will be less than epsilon whenever this h is less than delta. Since this will come from the uniform continuity of G, because G is an element in V and V is the collection of all bounded uniformly continuous function. Since G is uniformly continuous, this implies for epsilon positive there exists delta positive, such that this mod G psi minus Gx will be less than epsilon whenever mod psi minus x is less than delta. Now since this xi minus x, see, xi was in x to x plus h, that means xi minus x is always less than h. Mod xi minus x is less than h. So if h is less than delta, we get mod xi minus x less than delta, and hence mod gx minus g xi minus gx will be less than epsilon. That means limit h tending to 0, fx plus h minus fx upon h is equal to gx. That means limit h tending to 0, phi h f at any point x is equal to gx. In fact, yeah, sorry. This the what we already had. Now we need to show the uniform convergence. Now this epsilon and delta are independent of x, so we can take supremum. Now since this delta and epsilon are independent of x and xi, we get supremum x in R mod fx plus h minus fx upon h minus gx. This is less than epsilon. Yeah. Whenever whenever mod h is less than delta. That means this, yeah, because this is phi h f at x. So phi h f minus g sup norm goes to 0 as h goes to 0. Or we can say that this phi h f goes to g in v as h goes to 0, which implies that this f belongs to W. I hope this proof is fine. If you have any doubt at any step, please ask. I'll wait for 5 minutes. So we can consider this to be the last problem for today. After that, we can end this session. If please, you are free to ask whatever doubt you have at any point. Okay, so if there is no doubt, we can end this session. I hope this course was some a bit useful for you and you got something. Yeah. Okay then. Thank you.